So bound to bend it, or just bend it? I'm not sure of this, and I don't want to break it. Oh, it's the down thing. Thank you. All right. Back. Yes. So, welcome everyone back to the lecture. So today's lecture is going to really be about information in thermodynamics. The main content of the lecture will be Maxwell's demon, which was a very old but very thoroughly thought about thought experiment to sort of indicate that information can be used in a thermodynamic way. And historically, many people have discussed it to the point that a few decades ago, we finally understood why information is to be understood thermodynamically, and it has to do with the role of memory. Wherever we store information has to be treated thermodynamically. All right, but to begin the class, I will actually discuss a relationship between information entropy and thermal entropy, which follows directly from what we did last class on Jane's principle. And the thought is the following. So imagine that I take a state which is thermal. So I know that rho is e to the minus beta times h, which is the same as writing it as the sum over n of e to the minus beta en upon z, the partition function. And now what I do is I consider the following. I give this state a little bit of energy. So I increase the energy, the average energy by a differential amount of energy. So I say dE, and I keep it thermal. So this is really a consequence of using Jane's principle. So what I'm saying is, even though I exchange energy with the system, I'm always going to assume that I only know about the amount of energy exchanged, and other than that, the information in this system is the information I have about the state is the least possible, which is the same as maximizing its entropy. And as a consequence of this, I know then, since I will stay thermal, I can say that beta goes to beta plus some differential change in the temperature. Okay, so now what I want to do is I just want to write this equation. Now, what do I have? I say, well, let me differentiate the entropy. So, ds by d beta, and this is minus d by d beta sum pn log pn. So by pn I mean, so pn is e to the minus beta en by z. Okay, and now I just differentiate all of this minus sum over n, and I have 1 plus log pn d pn by d beta. This is just the rules of differentiation. Okay, the first term I can ignore, and the reason is because if it's just going to be sum over dpn by d beta, which is going to give me the differential of the sum over pn, and pn is a normalized property distribution. The sum is always 1, so the sum over pn doesn't change. So the second one is the one I'm interested in, and this one now I can expand. So log of pn is minus beta en minus log of z, and then I have dpn by beta. Okay, and just to say, the reason is because d over d beta of sum over Pn is equal to 0, because that is a constant. Okay, I can apply the same trick again here. The log z is just a constant that goes out of the sum. So that one again is going to give me the same thing. And I'm only left with this term. So this is now beta. And now I can write this as d over d beta of the sum over Pn, because En is a constant. So that can go in and out of the differential. And this is beta times d over d beta of the average energy. Okay. So set this on top. Sorry. Okay, and now I just do some semantics. I say whenever I exchange heat with a state that keeps on obeying James' principle, so it stays thermal. Sorry, whenever I exchange, I jumped the gun there. Whenever I exchange energy with a state that stays thermal, I'm going to call it heat. So I'm going to call d of average energy, I'm going to call it the differential heat that is exchanged with the system. And then what I get is the well-known formula, ds is equal to beta times dq, or dq over t, kt, which is the same as ds. And now this I can call ds information, because it's really from the von Neumann, but this is the definition of thermal entropy, dq over t. Now I have a 1 over k here, and the reason is because when I started with the definition of S, I didn't multiply by k. For the rest of the course, whenever I take the entropy, I will always consider it to be multiplied by k so that it links to the thermal entropy. But at the moment, it's just a proportionality constant. Right. So this now links the information and thermal entropy. The very important part there is Jane's principle. Otherwise, I cannot really write beta goes to beta plus a small change, because if I go to a state that's not thermal, then I cannot differentiate with respect to temperature. So it's only with Jane's principle do we get the exact link here. Okay, now the next thing to note is, of course, this is a differential equation. So it's not the same as saying any change in energy, finite change in the heat divided by temperature is the finite change in the entropy, because as I change the energy, the temperature is going to change. So a single thermal state will, after a finite amount of energy that I give it, its temperature will change. If, however, I have a thermal bath, and this is now the notion of the ideal thermal bath. So its energy capacity, or the heat capacity, let's say, is essentially large enough that as much energy that you give it, it does not actually gain temperature. This will be one of your tutorial questions to see how the heat capacity of n independent systems, for example, scales. If I, instead of giving one system energy, I split it among n copies of the thermal state, you see that then the temperature will change less. And so when I have an ideal thermal bath, so you have two things now. You have one is the heat capacity is infinity, and two always obeys, as usual, always obeys Jane's principle. And this is important. What this means is that whatever interactions I have with my bath, however complicated the bath might be, while the interactions are going on, I know from quantum theory that I will build up correlations between the system that's interacting with the bath, between the different components of the bath. But the assumption of an ideal thermal bath is that those correlations are always lost because of the complexity. We lose track of them. And so we always have to treat the bath as if we have the least information about it. And when we have this, then indeed you can integrate that one because beta never changes, and you end up with delta S is really, delta S information is delta Q over the temperature of the bath. Right? Any questions? Oh. All right. So then I go on to the main content of this lecture. Maxwell's demon. So Maxwell's demon was a very nice thought experiment conceived by, as the name suggests, Maxwell. And the experiment is very simple. Imagine that you have a gas that's sitting in a box. And at first, the gas is at equilibrium. So there are lots of particles. They're all at thermal equilibrium. Then somebody places a partition in the box that divides the box into two parts with a little opening in the middle. And at that opening sits, well, let's say a demon. And I know my demon looks a bit like a cat. That's because I'm not very good at drawing, but it can also be a cat. Who knows? Maybe cats are demons. So what does the demon do? It sits at the partition and it watches the gas particles approach from either side. And what it does is that it allows it, when there is a particle that is slow on the left-hand side, it allows it to go to the right-hand side. When there's a particle that is fast on the right-hand side, it allows it to go on the left-hand side. So what's going to happen is you're going to have hot particles here, so the ones that move faster, but it wants to concentrate the ones that move slower on the right-hand side. And so now imagine that the demon keeps doing this. Well, at the end of the day, what you're going to have is a hot gas on the left and a cold gas on the right. But these are two different temperatures now, and we can run a thermal engine between them. We can use them to, well, the heat flow between them would power any thermodynamic process that we want. And so now we have an apparent contradiction of the second law. We started with something that's entirely at equilibrium, and we've taken it out of equilibrium, from which we can also extract work. So this was the first sort of presentation of the thought experiment. About half a century after it was first thought of, the scientist Leo Szilard clarified the experiment by really reducing it to its essentials. And this is where we see now the link with information. So Szilard thought of a little engine that could be constructed from this experiment. Okay, I'm not going to have the space, so let's go here. And the Szilard engine is very simple. I have the same thing now, but instead of a big gas, I have only one single particle. So there's one particle that is roaming around in this box. We don't know where it is at first. The first thing that we do is we put a partition in the box. We still don't know where the particle is. It could be the left or the right. But then my demon comes along and it looks at where the particle is. So for example, imagine that we see that the particle is on the right. Okay, so now we know that the particle is on the right. What can we do with this? Well, imagine that this partition is not a fixed one, but it's a movable one that we can connect to a piston that can move and do work. So for example, I will just connect it to a weight. And so now if I allow the partition to move, we can in fact raise the weight by using the fact that this particle on the right is bouncing off these walls and there's nothing on the left. And so this is now just normal thermodynamic work. I'm going to use the pressure of this one particle to push the partition all the way from the middle to the left. And in doing so, I'm going to do work. Now I consider, well, how much work am I going to get out of this? Well, this is just a normal PV work. So what do I have? I'm going to have W is equal to the integral of P dV. And now the second step is to consider that all of this sits in an environment of, I won't call this, I'm going to say that the entire environment of this is some T. So all of this is thermalized to a temperature T, or at least the particle in the box is. Therefore, I can use now the equation for the ideal gas, P dV. This is going to be KT upon V dV, which is going to be KT log of V final upon V initial, which is KT log 2. Okay, right. Yes, so what we see here is that by knowing which part of the box the particle is, we can extract KT log 2 of work. And this is important because log 2 is exactly 1 bit of information. So delta S, which is 1 bit. This is exactly the amount of information that we start off knowing. So when we enter and the demon hasn't looked at the box, the particle can be left or right. So its entropy, if we look at the Shannon entropy of this, it's actually log 2. It's half log half plus half log half. Then they look at it and they know that it's on the right, so the Shannon entropy is now 0. But then when the particle moves the whole thing to the left, we end up in the initial state again, and so the entropy has increased to 1 bit again. So somehow what we have managed to do is we've exchanged 1 bit of entropy for KT log 2 of work. And so this really now boils down Maxwell's demon to saying, information about a system is actually tradable with work if I use a thermal environment. Okay, any questions? Oh. Oh, it's cleaning time. Are we? Yes. Okay. So, what is the solution to this paradox? Well, the first person to suggest in the direction of the solution without really formally going through the details was Landauer, which is why there's the corresponding term Landauer erasure. And what he did was to basically point out that what we have to do is to consider that the daemon itself is actually a thermodynamic entity. In particular, the memory of the daemon is a thermodynamic entity. So he gave some arguments in favor of this. It's not clear whether his argument was also cyclic in the sense that it required the second law. In any case, it is considered that Charles Bennett in the 80s sort of concluded the resolve this paradox once and for all by really going through the steps that the daemon's memory has to go through. So what do we mean by the daemon's memory? Well, so we start, now I'm going to quantify the information we have about different systems here. So we start with the system. I'm going to consider the system as just being a qubit that can be in left or right. There's no coherence, so it starts off before the daemon looks at it as just a mixture of left, left, and right, right, upon 2. So it's a fully mixed state. The daemon, on the other hand, starts with some memory state. And so it begins with, so the memory of the daemon, let's say rho of the memory is just some pure state of the memory. And the first thing that the daemon has to do is to measure what state the system is in. And this is done by something you're very familiar with. It's a C0 gate. We want to write whether this is left or right onto the state of the memory. So the first thing we do is to have a C0 gate, and that gives us the state, the correlated state now, left 0. No, let's put it this way. Left, left, tensor 0, 0, plus right, right, tensor 1, 1, memory system upon 2. So this is now rho, system, and memory. Right. The first question you might ask is, why do we need this measurement? And the reason is because you see there, when I attached the weight, I had to attach it to the correct side. If the particle was on the right, then what I've done is correct. But if the particle was on the left, then I would have to attach it on the left-hand side. So basically, the work extraction part of this, where I actually gain useful quantity from the information I have, depends on the state that I've measured. which means that I really need some system to actually act as a switch to tell me, oh, I'm extracting work in this manner or that manner. And that system has to write down the information of where my system, well, where the state of the particle is. This is why I need the memory of the daemon. The memory of the daemon is going to act as a switch for the next step. And so it itself must encode the information about where the particle is. Therefore, if the particle is left, my daemon's memory stays 0. If the particle is right, my daemon's memory stays 1. Okay, so that's the first thing. The second question you could ask is, well, why does the memory have to start in a pure state, for example? Can the memory start in a mixed state? What happens then? And here is very important, is the notion of reversibility, which is the same as unitarity. We know that when we consider evolution of a system in physics, as long as we consider all of the components that are involved so that we have a closed and isolated system, everything is reversible. You can write it as a unitary, which is the same as saying it's reversible, which is the same, I mean, when it comes to finite states, this is really bijective, so it's a one-to-one map. This is why a unitary can be written as I pick an orthonormal basis, and that orthonormal basis rotates into another orthonormal basis. Every orthonormal state goes to another orthonormal state. Okay, so what does this mean? You see here, I chose this state to start in 0, but I didn't need to do this. I could start it in any pure state X, for example. But what I do need is that no matter what the state of the memory starts in, when the system is left, I should get left on the system 0 of the memory. Because I've already designated that my next step is going to be 0 of the memory does one work extraction, 1 of the memory does another work extraction. But if X, so if X tensor L goes to 0 tensor L, and sorry, I'm going to keep the subscripts because I've switched the thing now, then it follows that no other state of the memory together with L can also go here, because that will not be reversible. That's not a one-to-one map. So therefore, it has to be that this starts in a pure state, because if it starts with a mixture of 0, for example, and 1, or if I choose a general X and then X orthogonal, I'm going to get some terms here that are not going to be of this form. So it could be that the system started with left, but the memory has not ended in 0, because it is impossible for everything that starts with left to end up with 0L. Okay, so this is very important. Reversibility prevents us from cheating with the memory. Okay, so what is the next step? So that's that step. And then the next step we have, and this is the work extraction. And in the work extraction, what happens, you can look at the top thing again, because the particle has pushed the partition to the left, we end up with the original state of the system where we didn't know whether it was left or right. So we end up once again in identity system over 2. This is, by the way, the same as the initial state. So I could write this as identity system over 2. It's the same as the maximally mixed state over the two states. And now, since the work extraction is on the system, the memory at the end, imagine now I took the state of the system and I made it identity over 2 and I left the memory unchanged, we would get identity memory over 2. And now this is here also very important. You could ask the question, well, why is it not the case that with the work extraction, my system goes back to the initial state, but my memory as well goes back to the initial state? And once again, reversibility will prevent you from doing that, because, sorry, just have to remind myself of something here. Made a mistake. No. Yes, sorry. If it is the case that left of the system with 0 of the memory goes to identity of the system, we cannot, if I put here that the memory goes to 0, what we would have is again a many-to-one map. We would have many states of the system and memory go to the same state of the memory. And this is something that you would have to also include the system that does the work extraction to get the complete way of looking that is a many-to-one map. We will not need this, because the next step that I'm going to do is to prove formally that all of these statements are true and to show exactly what the entropy change is. But again, here, the important part is that this is made necessary by reversibility. Okay, and then the end result now is that yes, we've extracted work. Our system has gone from unknown to known to unknown again, but a very big important change is that we started in the pure state of the memory and we've ended up with a mixed state of the memory. And so now I cannot use that memory to do this whole process again. It's not an indefinite work extraction process. If I want to do the whole thing again, I'd have to use a new bit of the memory, or I would have to reset this memory back to that. And that is exactly what is called an erasure. So if I want to reset this back to the 0 state of the memory, this is called erasure. And as you might expect, the cost of doing this is exactly equal or more than the work extracted in the first step. Okay, so now what I'm going to do is, this was a intuitive explanation, but what I will do next is a very neat, oh this is going to be difficult. Yeah.
What is the work extraction?
Oh. Yes, so I think I'm not sure I can answer this question very well without doing the formal proof of the whole thing. So I think it would possibly be better for me to just do the formal proof and then see that the entropy of the various components has to increase by a certain amount. So it doesn't have to exactly be that process that ended up with tensor product of two identities, but there's going to be a necessary entropy increase, as we shall see. Okay, so now we're going to prove the statements we made in the last part formally. So I'm going to now formally define what I'm going to do. So we have a state. First, we have the three components. So we have a system. We have a memory. And we have a bath. Okay, so the system is what I'm observing and writing the information on something else. We have the memory, and then we have the bath. Okay, so what do we do with these? We start, so initial state is some state of the system, memory, and bath, but independent and uncorrelated. So I start with some rho S and B, which is rho S, tensor rho M, tensor rho B. Now this is important because the assumption is that before I even start this thought experiment, there's no information yet. So there are no correlations. They've not been interacting with each other. If they were, then I would, of course, already have an advantage at the beginning. So we start in the beginning with the assumption that they're all uncorrelated. Then what do we do? Well, we do, for example, in the thing above, we would first do a unitary USM, which is to measure S. So let's call this U1. And then there would be a U2, which would have S, M, and possibly the bath, which is the work extraction. But the useful thing about unitaries is that if I do two unitaries consecutively on a state, I can also write this as one big unitary because the product of unitaries is also unitary. So the whole thing now I'm just going to consider as one big unitary U, S, M, and P. Okay. So the end result of this is that I go from this one to a unitary, to U, S, M, B, rho S, M, B, U dagger S, M, B. And now remember, this unitary represents the whole process. So it's all of the steps right from the part where I started to the part where I measured, I did the work extraction, and I end up with something, and I want to see, well, what can my system and the memory be at the end? Okay. This proof I will need to use notes. So the first step now is we look at the entropy. So the initial entropy, I will write this as ooh. Okay, so I'll have to trust that you differentiate between when I write S as a subscript for the system and S as entropy, which is a big S. But this is the initial entropy of the system. Because the initial system is a tensor product of systems, and I hope this is something you're used to, the entropy is just additive. This is S of rho S plus S of rho M plus S of rho B. Okay. And then I have the final entropy, which is just rho prime S and P. So this is something we don't know because the final state can, of course, be correlated, and in general is going to be correlated between S, M, and B. But what I can do is I can write down that the final thing minus, so this one, minus S of rho and B. I can have an expression for this by using the notion of mutual information. So just to remind you, the mutual information I, S, M, B is just the difference between S of rho S plus S of rho M plus S of rho B minus S of rho S and B. So this is now just a definition of mutual information. You add up the entropies of the marginal states and you subtract the entropy of the joint state. This is something that I expect you have seen in QIT, yes? Mutual information, right? Okay. The most important thing about the mutual information is that it's always positive because the entropy of the marginals, you always lose some information in the marginals. So if you sum up the entropy of the marginals, you always get something that is bigger than the entropy of the joint state. Okay, so rho prime S, yeah, sorry, let me just take this away. Now, what did you do? We started with a state that is a product state. So we know that the initial entropy is just the sum of those. So it's another way of saying the mutual information in the beginning is 0. The final entropy of the joint state we know is equal to the initial entropy of the joint state. And this is because of unitarity. The thing that we did was a unitary operation. So the entropy of the joint state does not change because entropy does not change under unitary operation. However, now when we look at the marginals, this, if I now, the final entropy of the joint state, I can put it in terms of the entropy of the marginals. So this is going to be, did I use S prime? Yeah. Is equal to, so S of rho prime S plus S of rho M prime plus S of rho B prime minus I SMB is equal to S of rho M, the entropy of the joint state, which now I break down as the sum of each. Okay, and now I've replaced on the left-hand side. I've used the definition of mutual information to just replace it. On the right-hand side, the mutual information is 0. The initial state's entropy is just the sum of the marginals. And now what I can do is I can write each change in entropy. So S of the final state of the system minus S of the initial state of the system. I'm just going to relabel it as delta S, the change in entropy of the system. And the whole thing that I get then is that delta S of the system plus delta S of the memory plus delta S of the bath is equal to I of system M bath, which of course is greater or equal to 0. That's the property of the mutual information. Are there any questions? Good, very good. Okay, so now what I'm going to do is I'm going to take each of these things. Well, in particular, delta S of the bath. This is something that you can use the definition of the entropy of, well, you can use the definition of the thermal state to actually calculate. This is, of course, S is defined as the Voigt-Neumann entropy. I'm not going to prove this statement. Not sure if it's in the tutorial or not, but even if it's not, it's definitely in the lecture notes, and I would highly recommend you prove this. It's equal to beta times EB, E of the bath, minus D of OB prime, OB. So this is only if rho B is thermal, so it's e to the minus beta HB on the partition functions. So when you have that the initial state is thermal, you can put it in this form. Delta SB is this. Okay, now just to say, EB is, as you know, it's a change in average energy. And just as a reminder, this is the quantum relative entropy. So it's trace of rho B prime log of rho B prime minus log of rho B. Okay, that's the quantum relative entropy, which gives us our final thing that we were heading for. Now I rewrite that, and I get delta SS plus delta SM plus delta SB. So is it, let's say, plus delta beta, sorry, beta delta EB is equal to, I have I, S, M, B, and I take the D on the other side as well, so plus D of rho B prime versus rho B. Okay, and this, very importantly, is greater or equal to 0. Yeah, I forgot to point out also, the relative entropy is a quantity that is always greater or equal to 0. This is also true for the quantum relative entropy. So on the right-hand side here, we have the mutual information and the quantum relative entropy, and they are both greater or equal to 0. Yes?
How is the mutual information of three systems actually defined? I only know the definition for two systems and conditional.
Well, so the definition is the one I wrote in green. So you really just, it's just the sum of the marginals minus the entropy. Yeah, the entropy of the marginal summed minus the entropy of the joint. Yeah, and it is 0 exactly when you have a product state. Yeah. Yes. Right. So this is greater or equal to 0, and so now, and the final step here is to say, well, what about the system? The point about using Maxwell's daemon is I start with the system in a state, I gain some information about it, I use the information to extract work, and that ends up with the system being in the original state that it was in. So I want rho prime of s to be equal to rho s. So what I'm going to do is I'm going to set this equal to 0, since so this is basically cyclicity. My system is acting like a cyclic engine, and so rho prime of s is equal to rho s. And so that in the end gives us a statement that delta Sm is greater or equal to minus beta delta Eb. Okay, and this is now the equation we're trying to go for, because if I wanted to transform heat into work, which is the whole point of, well, the Szilard engine is not there anymore, but what I did in the Szilard engine is I transformed heat into work. The particle absorbs heat from the environment and provides and converts it into useful work, and that was the KT log 2 that I got. Then I basically want delta Eb to be negative, because I've extracted heat from the bath and I've put it as work. This is the violation we're trying. But if delta Eb is negative, this is a positive quantity, and my increase in entropy has to be at least as much as that positive quantity. Okay. So this is where we have the solution to Maxwell's daemon. And what is very easy to verify is, so imagine now there are two things I can do. I can say, well, okay, I started with the first step in Maxwell's daemon, but now at the end of it, I have some correlations between my system, my memory, and my path. So maybe now if I repeated the whole procedure and I did Maxwell's daemon, the process of the Szilard engine again, maybe now I'm not actually constrained by this and I can do something better. This also doesn't work, because if I do something more, I can just write it as different unitaries again, like a third unitary and a fourth unitary and a fifth unitary. And all of that together is always going to be able to be written as one single unitary. So no matter how many steps I concatenate, I'm always going to be able to join all of that as one unitary, and this equation is always going to apply. So no matter how many steps I do, I'm always going to be bound by this one. This also immediately shows you why I cannot do this trick to extract as much of work as possible, because delta S is bounded. Like if I have a d-dimensional system that I use as a memory, then delta Sm, this is of course Sm itself is less or equal to log of dm, which is the dimension of the memory. So this also says that if the daemon starts with 10 bits of memory, then we can of course do 10 times KT log 2 and get work, but it always comes at a cost of increasing the entropy of the memory. And the final thing I can do now is to say, well, imagine that I did this whole thing to extract work, but then I used Maxwell's daemon again on the memory and tried to reset it back to its original state. So my first step would be to extract work. My second step would be to try and get rid of the entropy increase in this. Well, then I could again repeat this whole procedure, because the reverse of a unitary is also unitary. I'm going to get the same thing here. I can write it as, in some sense, I can write the second step as delta Sm. Oh. Beta delta Eb is greater or equal to minus delta Sm. This is just the same as this equation, but now it's just written in a form where I go, well, actually I'm trying to decrease the entropy of the memory. So this is now a negative quantity. This whole thing is a positive quantity. But then again, I see if I'm decreasing the entropy of the memory, this requires me to dissipate heat into the bath. And this dissipation of heat, of course, comes from somewhere. It has to be work that is now dissipated into heat, because the unitary is the thing that provides the energy change for this whole process. And then, of course, if I sum these two things together, I can call this prime and prime to say that they're two different processes. If I sum these two things together, I'm going to get the original thing. So if I sum these two things together and I say, well, I want the memory to be put back into its original state, then I would get, so the sum would be delta Sm plus delta Sm prime, and I want this to be 0 so that my memory is back to the original state, is going to be greater or equal to minus beta delta Eb plus delta Eb prime. And this is now back again our second law. I've done a cyclic process, not only on the system, but also on the memory. But that immediately means that my heat, so this whole term has, if this is 0 greater than this whole thing, that means that this whole thing inside the parenthesis has to be positive, which means that in the end, I will have put in heat to the bath. So I would have taken work and put in and converted it to heat. So any cyclic process is always still going to obey the second law. And yes, so the take-home message from all of this is that information about systems has a thermodynamic meaning and a thermodynamic usefulness, because we can trade it for work and heat with processes such as these. In the next lecture, what we will do is now invert all of this and talk about how exactly we're going to do these steps. So these were all to determine sort of what the bounds on what we can do are. But in the next lecture, we are going to take actual protocols that do these things. So in one case, it will do the process of erasure. I will have a memory that I start in a mixed state. I want to convert it to a pure state, and I want to see what are the exact operations we are going to need to do that. So this is where the qubit swap is going to come back, and we're going to use that very heavily. And then, of course, the inverse process where I have a system, I have some amount of information, so my memory is in a pure state, or I know information about my system, and I use that to extract work, which will just be the reverse of the process. The other thing we will do next week, which we haven't done this time, is to actually consider the work source as an explicit system. So everything I've done so far, what I've done is I've said we do some unitary operation, and clearly the unitary operation is going to change the energy of the different components. So the assumption here is that whatever the change in energy is, it's being provided by the apparatus that does the unitary operation. But we can take this away by actually including an extra system in there, which we call W for work. And then that work source will be the one that provides the energy to the rest. So the global unitary then will be energy preserving, because the energy that we need for the system, memory, and bath will come from an explicit system that we include. All right, I'll conclude here. Any more questions or thoughts about this? None? Perfect. Then I will see you next week. Thank you.